Go to the petroleum industry. They understand mud. They use it in their drilling, and they also understand it from drilling into it. And I'm going to show you some documentation on it. All right, in order to understand the mud fossils, you have to understand mud, and very few of the academics I've talked to do. The people that do understand it are the drilling industry, the deep well people that drill way down deep, because they use mud and clay in the drilling process, and of course they drill through it. And clay it's right here. This is by them, by a company, Geo Drilling Fluids Inc. Clay is a mineral, either a rock or a soil, that becomes plastic. It becomes plastic and ductile. It doesn't spring back. It becomes plastic. It flattens out when it's wet. Property is the result of the small particle size, tiny, molecular virtually, and the plate-like nature of the particles. They're little flat, they're like shingles. Most clays become sticky and slippery when they get wetted, but only a few clays actually swell to the same degree as Wyoming bentonite. And obviously that's what they use for their drilling to plug the wells, because the wells get spoiled by these clays and they need to evacuate them. Here's it says right here, almost all drilling fluids contain some clays. That's the fluid they pump in. And the mud business, clays are an essential ingredient in almost all drilling fluids, yet they are also one of the most common contaminants. Muds contaminate the drills, and they seize them up. So they need to use something to evacuate all that stuff. So excessive amounts of clay cause problems with rheology and density. This situation is very prolific in California. So anyway, I'm going to show you a little more about this deeper into this article. All right, it continues on. This gets very detailed. It says the technical definition of clay involves the molecular structure, a material that has loosely bonded layers which are only molecules thick, is generally classified as a clay. And they end up creating these crystals because they are also polar. Some clays absorb a great deal of water, and then they go into the drilling aspects of this. But I'm talking about the molecular transfer under ionic conditions creates feldspar, and that's what these clays do. That's exactly what they do. All right, and here's the smoking gun right here, the family of clay minerals. Amorphous clays are in a group called aliphanes. The makeup of these clays is silica, tetrahedrons, and aluminum octahedrons intermixed with crystalline material. The alloplane clays have little or no discernible structure. They seem to be a precursor to the more structured clays. That's exactly what happens. Anyway, it goes on. Cation exchange capacity. This is exactly the reason that soft tissues, organic tissues who are extremely reactive, become penetrated by these platy little tiny molecular silicates that are flat little plates, and they create crystals by just the nature of how they accumulate. All right? Cation exchange capacity measures the exchangeable cations, and anions also can be exchanged, but they are not as well understood. Those are the positive and negative ions that are reacting with the extremely reactive substances that are in soft tissues that are encapsulated in these muds. And these muds are also acted on by electrical potentials. Now it says the size of these various cations determines how readily they are exchanged and how lightly it is held once replaced. Figure 11, The larger the non-hydrated size of the cation, the more easily it drives out the existing cation. So the cation comes in, it says, I'm tougher than you, you little guys get out, I'm coming in. It's a whole different element. In addition, the smaller the hydrated size of the ions, the more strongly it holds onto its position in the clay matrix. Tetrahedral sheets form a series, listen to this now, of holes which perfectly match the potassium ion size, such that once it has replaced sodium or calcium, it is very hard to displace. This helps explain the importance of K plus in the long-term inhibition of clays. This is what goes into organic materials, displaces them, and turns them into stone, for quartzite, into the platy little silicate crystals. And I have recreated this process. And if you look at electrofossilization, you'll see exactly how it's done. And it's a very simple process, and the earth currents are totally understood. The process is just simple and totally understood, and the head has absolutely no other alternative other than that's what happened here. There's nothing, and we're totally open to anybody else, but there's nobody could come up with anything, nothing, zero. And I can't possibly think of any other, I mean, we really tried. We thought of everything. Because, you know, you want to stand on good solid ground, and the solidest ground we're on is like solid rock, man. Nobody can possibly come up with anything else that I can possibly think of. I'm open. But that's what I want to hear. All right, this is a little more about the molecular forces that replace things. Now, and it talks about bonding of the particles within the clay are caused by these different forces. And there's the mass of gravity, obviously, we all understand that. Overlapping molecular forces. Those are van der Waals forces and Pauli principle stuff, where the molecular orbits are interfering with each other, and then they bond in a certain way, or they repel in a certain way. But these are the kind of forces that deep in the earth are you have to take into consideration. Cation attraction, pulling two platelets together. That's this ionic interreaction. It's also called nucleophilic reaction. There's nucleophiles and there's electrophiles, and they have leaving groups and entering groups. And it's just a process that is totally understood. Water molecules, 1 to 3 molecules thick, attracting the two platelets to one another. Water molecules are one of the smallest molecule there is. There's the 2 hydrogens and an oxygen. That's it. Every other molecule virtually is bigger. I mean, there is some that are small, OH and stuff like that. But anyway, they're tiny. And so that's what's going on here. Clays with the same chemical constituents may have very different properties, and clays with identical properties may have very different chemical constituents. It all depends on what's in the clays is what gets attracted to these polar little silicate interactions. And the resident material, which is the organic material, sometimes will turn into all kinds of crazy things like opals. Opals are the result of this exact same process. Exact same process. So they started out as living entities, and percolation of some material that is prevalent in opals was invaded the original organic material. That's exactly how it happens. And I don't think anybody's disputing that either. They just don't understand the meaning of this head. It's just too much for them to work with. So anyway, that's what's going on here. And then it goes on and on and on and on. So anyway, that's what it is.